Thank you, David. It's great to be back in Bonn. I see Werner Hildebrand sitting there. I can remember being here many years back in the 1980s and 90s at visiting Werner Hildebrand's group. And I've truly enjoyed myself over the last couple of days at the Panorama. I'm learning a lot. What I'm going to try to impart today are some of the action that's going on in both mathematical modeling and out there in the world of policy on regulation with respect to information that you can get from financial prices in markets for bonds, foreign exchange, swaps, which are forms of derivatives, and so on. Just to warm you up to the idea, you're probably most used to thinking about financial markets as a place where various market participants go and trade in a central exchange. But in fact, all of the financial instruments that I just mentioned, which constitute more than half of what's traded, are not traded on an exchange. They're traded over the counter, meaning you have to go find someone with whom to trade and negotiate the price. And it's been a long-standing program of financial economists and economists generally to understand this process of discovering from prices information about the value of the underlying asset. This goes back to work by Friedrich von Hayek, a famous Austrian economist in the 1940s. And there's work going on all the time in this area. Yesterday I spoke to Professor Stefan Lauermann here in Bonn, and he's doing some of the fundamental work in this area. Some of the work that I'm going to talk about today is related to getting a price from a dealer, which is a designated market participant, usually a large bank, and you have some in Germany, you have some in London, some in New York. These large banks provide price offers and bids that you may accept, or you have the outside option to continue shopping among other market participants. And towards the end of my talk, I'll explain how the prices that have been offered by dealers have been manipulated. You've heard, I'm sure, about some of the scandals associated with LIBOR, Euribor, foreign exchange markets. I'll come back to that later. That's important for a number of reasons. Of course, the obvious reason is that it's an issue of honesty and integrity and reliance and trust. But it's also an important issue from the viewpoint of getting correct information from prices. And I'll hopefully be able to explain why that's very important in getting an efficient allocation of financial instruments, risk, liquidity, and so on. Just to give you an idea about how difficult it is to know what the going price is for a financial instrument, I'm plotting here on this chart the prices at which a specific bond, a municipal bond in the United States, was traded on each day after it was issued. And this, by the way, is not an unusual or pathological case, but if you look at the numbers on the vertical axis, you would almost not believe that some investors are paying 2 or 3% or more of the value of the bond, more than other investors are paying for the same bond on the same day. This is not because the price is moving up and down a lot during the day. No, it's because some investors are well informed about the true value of the bond, and other investors really have very little idea of what the bond is worth. So when a bank offers to sell the bond at 105, some investors will say, I'll buy it. Other investors will say no, and they'll shop for a better price at a different bank. And this typifies what financial economists call over-the-counter markets, where you must shop around looking for a good price, in many cases not being aware of what a good price is. You don't know where to shop, and you don't know what price to accept when you see the price. This is a market that I've studied with a collaborator, Adam Ashcraft, at the Federal Reserve Bank of New York, which is called the federal funds market. This is the market for banks to borrow money overnight, or for terms like 1 or 2 or 3 weeks, from each other. And this market has a very natural network structure which is called core periphery, where a number of large banks do a lot of the trading, And then the banks just outside of those, in the periphery of those, do more trading, but in smaller amounts. And then there are the extreme periphery banks, the smaller ones, that trade least of all. And these banks tend to be connected towards the middle. And if I have some time, I'll make some reference to the importance of that core periphery structure. What it means is that the banks in the middle are most informed, and the banks on the outside are least informed. In the US, there are 7,000 banks. Similar studies, the chart that's drawn here is from work by Morten Beck. Similar studies have been done for German banks and for other European banking networks. It's a big topic, but today it's related to this issue of how does information flow through this market. I mentioned a moment ago that in the bond market, a bond may trade at 1% or 2% or 3% above what it should. In this market, the interest rates are 1/100th of a basis point, or 2/100ths of a percent, or 3/100ths of a percent higher than they should be if you got the best price. That's a factor of 100 smaller dispersion, but still it's very important because many billions of dollars are being traded. In fact, trillions of dollars are traded in this market. So even a small fraction of price dispersion could be very important. The real world of over-the-counter financial markets is changing rapidly because rather than shopping in a completely decentralized way, there are now more and more opportunities to get competition on small trading platforms, which are illustrated by black boxes in this chart. And unfortunately today I'm not going to be able to tell you much because economists are lagging way behind regulation and banking developments in the last few years, some of this structure is a result of new regulations coming out of the financial crisis. So as hard as we try, we can't seem to keep the models up to where the regulators are going, but we'll try to catch up. I mentioned some of the literature. I mentioned Friedrich von Hayek. There has been literature on price transmission in centralized markets, and then more recently, work on price information transmission in over-the-counter markets. And that last topic is the focus of my remarks today. And to do that, I'm going to start very simple. In a moment, I'm going to take us back to that completely decentralized market. In fact, let me show you it, where you contact investors one-on-one, you negotiate a price, or if you can't, then you move on and you try to find another investor with whom to negotiate a price. That's the basis of the first modeling, the first mathematical modeling that I'm going to do today. And then later, when we get to talk about LIBOR and Euribor and foreign exchange price manipulation, I'll come back to the dealer intermediated market where you go to a big bank instead of to one of many thousands or millions of other investors. And I'm going to try to leave time in about half an hour for you to ask me questions. So start thinking of your questions. I've learned a lot in the previous talks at Panorama just from listening to the give and take in the question and answer sessions. So here's the setup, and everything is going to be highly stylized in a mathematical way to make the modeling go very smoothly. And later, if we have time, I can talk about generalizations, but I'm going to keep it very simple. So we're going to start with a situation in which the set of investors is a non-atomic measure space. Why do I do that? Well, for reasons similar to what Werner Hildebrandt was doing many years ago in this area. If you take them to be non-atomic, then each will not be concerned about his or her own influence on the entire market. And that becomes very important. It reduces the amount of strategic behavior. If I know that I'm infinitesimal in the scheme of all investors, then I will behave in a less strategic way. So that's what we're going to do. It'll also give us the opportunity to take advantage of the law of large numbers because we're going to have an infinite number of investors over whom we're going to average to get the effect of the law of large numbers. Uncertainty is determined by a probability space, and each agent will be given a finite set of signals about the value of the underlying financial instrument. So if it's, let's say it's an ounce of gold, then you'll get, each of you in the room will get a signal or a package of signals about what the true value of the ounce of gold is. And then later you can go shopping around to buy or to sell, having been given that information. Each of these signals is either 1 meaning positive signal or 0 meaning a negative signal. And for the first, in fact, for all of the models that I'll work on for the next few minutes, I'll assume that the price of gold is either high or low. That makes the equations very simple. You can make it more general with Gaussian distributions. It just takes a little bit longer to explain. So imagine that each of you has this package of signals, and you're going to start trading in a minute or so. But before we do that, let me mention that in order to take advantage of the law of large numbers, you have to be careful. We're going to assume that these signals, conditional on the true value of gold, these signals are independent. There's an infinite number of you out there, and now we have to be a little bit cautious, because if you have an infinite number of signals, in fact, there's a continuum, 0, 1 measure space of you. If you have an infinite number of investors, each holding conditionally independent signals, you got to be careful when applying the law of large numbers. Kolmogorov showed that you can't do that. You can't do that if you try to assume product measurability of the agent space and the probability space. So we're going to ditch product measurability. We're going to throw that out the window. We're going to add a little bit more to the sigma algebra on the state, the set omega of states of the world, and the set 0, 1 of agents. So we're going to add enough measurability that we can use the law of large numbers. And the idea for doing that comes from non-standard analysis and some work by one of my collaborators, Yanang Sun, who's at the National University of Singapore, who showed how you can, in fact, use the law of large numbers in this setting. Yanang was a student of Peter Loeb, and for those of you that know, Loeb figured out how to do this non-standard analysis stuff and then move it over into standard measure theory land where everything works nicely. So that's what we're going to do today. So you should be thinking in terms of what given your signals, each of you will hold some probability assignment that the value of gold is high today, and some other probability that it's low. It's a bit awkward to work in terms of these posterior probabilities, so we'll do it we'll model your current state of information as the log likelihood ratio of those two probabilities. That is, what's the log of the ratio of your conditional probabilities of high versus low gold, given your signals. And the reason we're going to do that is that it's going to make it easier to model the dynamics of how your information changes over time across the whole population in the room. So you all now can convert its equivalent information to convert to your log likelihood ratios, and I'll just call that your information type. So each of you has a type now, which is a number on the real line. And if the type is very high, then you think gold is worth a lot, and if your type is very low, then you'd think gold is not worth as much. It turns out that converting to types is a nice change of variables, because if I give you another package of signals that you might learn by trading, then the type that you will come away with, having learned the new signals, is just the sum of the type that you entered the trade with and the type of the new signals that you learned by trading. Let me repeat that. If you started with a type of 10 because you're an optimist, and you met someone with a type of minus 15 because she was a pessimist, you will both come away with the type minus 5, being moderately pessimistic. So that's a very easy way now to model the propagation of posterior probabilities in the population. Every time two agents randomly meet, they will make a bid or an offer in price terms. From each other, they will learn each other's type, because the price offered will reveal your type. When you offer a price of 1,000 euros for an ounce of gold, that will reveal your type. Your counterparty will likewise reveal the type, and you will both walk away with a new type that's the sum of the two types that you started with. Very simple modeling. That's the advantage of doing it this way. Okay, a little bit of let me not make you read this whole slide. I'll just tell you what's going to happen. We're going to start, the clock is starting, we're going to start trading with each other so everyone can think that you're going to stand up and randomly move around the room, bump into somebody at random, and whenever you bump into someone, you can negotiate to trade for an ounce of gold. And perhaps you won't reach a bargain, but then if you don't, you can go on and try to trade with someone else. This is a standard called matching or search and bargaining style analysis of OTC markets. The special thing that's going to happen here is when you bargain, you will reveal to each other your types. And then you'll walk away with more information, and we're interested in modeling how that information changes over time in the whole population. So what we're going to do is we're going to model a measure-valued stochastic process. In fact, my host at this conference, Carl Theodor Sturm, is an expert on these kinds of processes. We're going to model this measure-valued stochastic process which describes at each time, in each state of the world, what fraction of the population has a type below any given number. That's the measure that we're talking about. So for example, when you start, if the state of the world is high, then FH evaluated at a type Y is the fraction of the initial population that has a type of Y or below. So that's a measure. There's going to be one measure that applies when the true state is high. There's going to be another measure that applies when the true state is low. That means there's going to be, as time moves forward, these measures are going to get updated, and we're going to get a measure-valued stochastic process. Today it's going to be very easy to model because I've made everything very simple. Just for expositional reasons, it's not at all necessary. I'm going to assume that these measures have a density, which means they're absolutely continuous with respect to Lebesgue measure, which means that I can write down density equations more easily than I can write down more abstract equations. But we don't really need densities. So I'm going to do an example for you of how this measure-valued process evolves over time in just a moment. But let me set up the equations for this. I already told you that you're going to be bumping into each other at random. So literally speaking, each of you will meet another at a Poisson arrival time, a sequence of times which are separated by exponentially distributed waiting times. When you meet each other, you will exchange your information through bidding for the asset, and then you'll walk away and you'll meet other agents. These meeting times are going to be independent across the population, and in some work that I've done with a number of collaborators, including Yinang Sun, we can make this all work legitimately using proper stochastic analysis. There's no hand-waving here. In the end, the equation at the bottom of this slide describes the evolution of the density of types in the population. So this is a stochastic process. G of t is the density of types in the population at time t. It's a function of types. I'm just writing it as a function of time here, but it also depends on types. It gives you the density at each time. I'll show you a picture in a minute. And as time moves forward, this density changes in a very simple way, because I've made everything simple. The first term says that at rate minus lambda, the old density goes away because people are meeting each other at rate lambda. And when we apply the law of large numbers, we can get this equation to hold almost surely. The entire density function is losing its old density at rate lambda times the old density function, and it's being replaced with a new density function with rate lambda times g convolved with g. Why? Because remember, when two types meet, their types come away as the sum of the two. And what happens when you have two density functions, draw from them at random at rate lambda, and when you get two observations, you add them together? You're adding to the population at rate lambda times the convolution of this density with itself. If the intuition for that is not obvious, just think in terms of convolution means adding. This is now a very simple equation. You can think of it, for those of you that have studied mathematical physics, as a variant of the Boltzmann equation that describes the state of particles in a large population of particles in some medium, except in the Boltzmann equation, the last term, which is called the collision term, is more complicated. Today, the collision term is very simple. It's just convolution. And because of that, we're able to solve this equation, as you might guess. I'm sure that at least, given the types of people that are here today, at least half the people in the room could scream out what we should do in order to solve this equation. Does anybody want to scream out? Yeah, I heard it already. A few people murmured, Fourier transform. Absolutely. So if we take the Fourier transform of this, the first term, of course, is just going to be, on the right-hand side, is lambda times the Fourier transform. The second term, what happens when you take the Fourier of a convolution? Take product. So we're going to get lambda times the Fourier squared. So that's, first term is linear, second term is quadratic on the Fourier side. That's a Riccati equation. Now you can write down the solution. And I'll skip writing it down and just give you the solution. Once you reverse transform back to the real domain, the density of the population at type theta at time t is given by the solution of the inverse transform, which is an equation shown on the slide. And this equation actually does show up again in a more complicated way in the area of Boltzmann equations, except in this case we can actually write it down explicitly. In the area of Boltzmann equations, this is sometimes called a Wild sum, because there's a famous Russian mathematician named Wild that first proposed how to address these kinds of evolution equations. As far as I know, this is the only one you can write down really easily of the Boltzmann class. Okay, now I'm going to give you an example, just so that it's not all abstract. I'm going to start with the assumption that gold price is equally likely to be high or low. So that's the unconditional probability. And we're going to distribute among you all enough information initially that when the gold price is truly high, the initial density function is linear, going from none of you holding, let's just draw the picture. The initial density is the straight line on this picture. And I'm colorblind. I think that's purple. Is it purple? Anyway, the straight line picture is the initial density function when gold price is high. Of course, you don't know whether it's high or not, but that's what it is. And in the state of the world where it's low, it's just the reverse. It's the straight line is declining from 2 to 0 rather than rising from 0 to 2. And then over time, as you all meet each other, you bid for the price of gold with each other, and you learn from each other, because the true state of the world is high, or when it's high, the cross-sectional distribution of types in the population will start migrating to where more and more of you are coming to believe that it's very likely that the price of gold is in fact high. And over time, the cross-sectional distribution of types in the population will put more and more weight over towards all the probability being close to 1 that the price of gold is high. And we're going to eventually learn, just through trading, that that's the case. Now these cross-sectional density functions, the distribution of types in a population, of course converges exponentially fast. Anybody want to guess the rate? Of course it's lambda, the Poisson arrival rate of the meetings. So this density function converges exponentially at rate lambda, which is your individual meeting rates, as time moves forward. Okay, now I'm going to enlarge, make it a little bit more interesting, but I'm hoping that I've given you at least enough of a sense of the idea that merely by meeting each other one-on-one, eventually the wisdom of crowds, as is often said in English, the wisdom of crowds will cause you to collectively learn what the true price of gold is merely by trading with each other. That's how over-the-counter markets work. What happens if you meet, instead of one-on-one, you meet in small groups? I told you about trading platforms where small groups of market participants meet. So instead of meeting 2 at a time, suppose you met 3 at a time or 4 at a time. Well, you can write down the obvious equation. And the collision term now is, instead of being the convolution of G with itself, which is 2 meetings, it's the m-fold convolution where there are m at a time meeting. So if there are 3 of you meeting at a time, the last term is the convolution of G with itself 3 times. Do the Fourier again. Another change of variables, and you can solve the equation. And I'm going to show you a moving picture, sort of the evolution of types in the population with either 2 at a time or 3 at a time. So let's say 5 minutes from now, we look at the cross-sectional distribution of types, and it's shown in this diagram with a bar chart. So this is a case where we don't have a density. We have some atoms in the distribution. And the height of the bar is the fraction of you all in the room that have a information type corresponding to the point under that bar. There's 2 cases, one which you're meeting 2 at a time, that's in blue, and another case, a different world, in which investors are meeting 3 at a time. And after some passage of time, if gold is really very valuable, that distribution of types is going to move to the right as I click through these slides, and more of the population, that's you all, are holding higher and higher probabilities that the value of gold is quite high. And there it goes off to the right. Does anybody want to guess the exponential rate of convergence of this distribution to perfect knowledge? Nobody wants to blurt it out? It's, again, lambda. It's invariant to the number of individuals meeting in a group, which surprises some people. But of course, it's a different constant in front of the convergence rate. So we get convergence at rate lambda, where lambda is the meeting rate, and there everyone goes. Now, we don't have to have just such a simple model. We could have a model in which, as time goes on, you're continuing to gather information on your own, privately. That still works. I'm not going to write down the equation. It's just another term in the evolution equation. We can also have a model in which, at points in time, there's suddenly a burst of information that's publicly revealed to everyone. So that could be a transaction price announcement. And you can imagine what happens. When that happens, the entire distribution lifts, comes over, and drops down in a new place. But the whole distribution is shifting by the same amount in types, in the sense of types. You can also have variation across the population in your meeting speeds. Rather than just having a constant lambda, where everyone is meeting each other at rate lambda, we can vary that by whether you're a sophisticated hedge fund or whether you're a sleepy investor like me. I almost never trade. We can also give you the ability to choose how fast you want to trade. Of course, if you want to be a fast trader, you're going to have to invest more in your meeting technology. And that has an impact on the convergence. It also imposes what's called positive externalities or complementarities, meaning if this side of the room chooses to invest a lot in meeting quickly, then this side of the room will choose to do the same thing. But if this side of the room chooses to be lazy and not meet very much, then this side of the room will not find it worthwhile to invest in faster meeting technology, because when they meet with these guys over here, they won't learn that much. It's not worth it. So this is what economists call complementarities, strategic complementarities. We can also have, in new work that I'm doing with Lei Chao and Yineng Sun, directed search, meaning I don't just draw at random from the room when I search. I know perhaps that this side of the room has more valuable information or is more likely to have valuable information, so I try to shift my search technology to address more those that have more information to meet. And then the last one, which I'm working on right now, which is not going too well, so maybe I can encourage some of you to take over at this point, is search on networks. So the only case in which I can do this same kind of modeling on a network is where it's a tree-based network. There's no loops. Why? Well, because if you have a loop and you get a piece of information from someone, you don't know whether you might have already heard some of that information from somebody else. And that makes it really difficult to analyze. So if any of you can do this on a more general general graph than a tree, please go ahead and try to solve that. Okay, now I'm going to skip to these benchmarks that I told you at the beginning were manipulated. And let me remind you what the story was. It's a bit unfortunate. It's a sad story. It happened all across the world, including here in Germany, where large banks were telling lies about the prices at which they were trading and causing public information releases about price to be manipulated, to be distorted. And they did that for a number of reasons. In the case of LIBOR and Euribor, it's believed that the banks distorted their reports because they didn't want, in the financial crisis, to reveal that they were borrowing money at very high interest rates. Because if they were to say, I'm borrowing money at much higher interest rates than JP Morgan, then investors might be worried about whether those banks could continue to perform. It might raise their cost of getting new investments from shareholders. It may raise their cost for borrowing money. They lied. They didn't want to reveal that they were in fact borrowing at very high interest rates. The other type of manipulation is somebody trading derivatives would call me at the treasury desk of the bank and say, Darrell, would you mind, when you report the rate at which we're borrowing money today, to push it up higher than it really is so that I can profit on a derivatives transaction? Completely dishonest. I always take the opportunity with my classes at Stanford to say, just don't do it. But for some reason, not everybody gets that message, and there is some cheating that goes on. And I think it's incumbent on everybody to just keep repeating, this is not acceptable. Okay, so that's not mathematics, but as I mentioned, I always repeat it. It's not acceptable. You might think, well, LIBOR, okay, that's just interest rates. But the same thing happened in foreign exchange markets. The same thing has happened in oil markets. The same thing has happened in pharmaceuticals markets. And I mentioned gold. The same thing happened in gold markets, where these prices were distorted for various reasons, mostly to make profit. For the purposes of today's discussion, that is important because that means that as people learn about the true value of, say, gold over time, they're not getting correct information. And that means the prices at which they're trading are distorted, which means that the allocation of gold to investors is not proper. It's not efficient. And so getting those price benchmarks accurate is an important part of making the financial system work well. Here's an example of the amount of dependence in the Eurozone and the US there is on LIBOR or Euribor. Euribor, if you don't know, is the Eurozone analog of LIBOR. It's the interest rate at which large banks are borrowing money. That's what was distorted. And you can look at the magnitudes. These are in billions of dollars or billions of euros. So let's look at, for example, the big number, which is Eurozone derivatives, interest rate swaps. Those are derivatives. 137,000 billion, or also known as 137 trillion euros of derivatives. That's a lot. Trillion with a T. It's a big number. That means that many financial contracts were dependent on Euribor being an accurate number. And that's why the guy from the derivatives desk called me, because he had an enormous multi-trillion-dollar interest rate derivatives position. If I could move up my report, make it inaccurate by just 0.01%, multiplied by a couple of trillion notional position in derivatives, that's a big profit. So that's why the incentives are wrong. And I contributed to an international effort to improve the quality of these benchmarks and to provide alternative mechanisms for setting these benchmarks. That's a longer story. What I'm going to do in the last few minutes is to describe a very simple model in which, rather than trading with each other in a very large population, you're going to trade with a small number of banks, dealers, and you're going to look for the best price among a small number, maybe 5. And we're going to look at the importance of accurate benchmarks like Euribor or gold benchmarks in determining whether or not you're willing to make a trade, and to also determine how much effort you make in searching for a good price. So this is about searching for the best price among banks. And we're going to do it in two cases, very briefly. One in which there's a published benchmark that's accurate, like, for example, the gold fixing that's announced in London every day. And the other in which there is no benchmark, because the benchmark perhaps was never invented, or it was so put into such disrepute by manipulation that it was decommissioned and it went away. So this is a story about the value of having good benchmarks. Okay, so here are, you all don't know what these prices are. Let's say these are prices for some commodity that you want to buy. Maybe it's copper, for which also has a benchmark. And you haven't seen these prices yet. You're going to go shopping for the best price. And you're going to buy a pound of, or a kilo of copper, since we're in Europe. The banks are going to have a cost for getting the copper to sell to you, which includes a common component that's called the benchmark. C for common component, that's benchmark, plus a random bit that depends on the bank, because each bank is different. And remember, we have two options. One is to publish the benchmark, and the other is to keep it unpublished. And we're going to talk about how much better it is to publish the benchmark. That's the objective now. So improving the price transmission mechanism. Each dealer, when you approach dealer number 1, that dealer was going to give you a price of 2.1. That means they're willing to sell you copper at 2.1 per kilo. The next one, if you visit them, would be 1.9, and so on. You're just going to visit these dealers in random order. There's no better way to do it in this example, because all the epsilons, the independent parts, are independent. You'll just visit them in random order, and eventually you'll decide, okay, I'll just take the best price I've seen so far. The dealers are going to profit by their profit margin, which is the price that you pay minus their cost times the quantity of trades that they make. So they have an advantage in lowering their price to get more trade, but they also have a disadvantage, and that means lower profit margin. They're going to balance the two. So here's, for example, Sven is sitting in the front row. Here's one possible search path. Sven is a very fast guy. There's something called the diamond paradox, which means that we need to populate some of you with instant search speed. So that's Sven. He's really fast. Trust me, it's true. So he's able to canvass all 5 banks immediately and find the lowest price, which is 1.7. And he's going to buy at 1.7. Now, I'm the bank. I don't know when I see Sven that he's fast. So I'm going to trade off between it might be Sven or it might be somebody else that's not quite as quick. For the rest of us, which are slower, we're going to incur a delay cost every time we visit a new bank. And I know that some of you may have borrowed money to take out a student loan or to buy a house. I'm sure that you didn't visit all the banks in Germany or wherever you come from. You probably visited 1 or 2 because it's costly to search around. So we'll assume whatever the search cost is or delay cost for each successive search, we'll call it some number S. And for people like me that are slow, I might have done the following search. I might have visited the first bank. It said 2.1. I said, well, maybe that's good. I don't know. I'll visit the second bank, incurring another search cost. That bank said 1.9. I don't know what the benchmark is. Maybe I'll search one more. 2.2. I say, okay, that's enough. I've incurred enough search. I'll go back to the second bank and buy for 1.9. Now, that's not necessarily the best thing to do. And even if it were, the dealer quotes are going to take account of the strategies of the buyers, that's you all, in deciding what prices that they're going to bid or offer. And I'm just going to give you the answer rather than taking you through the analysis. Good thing, because we only have 5 minutes or so for me, and then the rest of the time is yours. If I were to have taken this search path, what would have happened? I would have acquired the kilogram of copper, which is worth V, a constant, which doesn't depend on who I am. I would have paid 1.9 euros to get it, and I would have incurred 3 search costs. So that's my payoff function. This isn't necessarily the right thing to do. Now this search problem, this kind of search problem was addressed a long time ago in work by Marty Weitzman, a Harvard economist. And it turns out that in this particular environment, there's a very simple algorithm for all of you to remember when you're doing a search of this type. And it's a bit surprising. The answer is a bit surprising. You might think that the more banks you visited and the fewer banks that are left, you're going to change the price that you'd be willing to accept. Because when you're down to the last bank or the second to last bank, you're saying to yourself, well, gosh, I'm running out of banks. Maybe I should take this price even though I wouldn't have taken it last time. No. Turns out that in this particular setting, you can pretend, it's optimal to pretend that the bank you're visiting is the next to last. There's only one more left. This is called the Pandora solution. This applies in general search problems of this type. So in the Pandora world, I can ignore how many banks are left. I can pretend that there's only one more left, and I can just compare. Do I take the price that the best price I've seen already, or do I take one more try, one more search? And if you just compare the two, that will determine the price you are willing to accept. The dealers have solved the problem that you're facing because they need to know how much to charge, and they're going to bear in mind your willingness to pay. And an equilibrium, a Nash equilibrium in which they're setting their prices optimally and you're searching optimally, is very simple to describe. What happens is that you're going to search just once in equilibrium, and the bank that you visit will always offer you a price that you're willing to accept. First time. That's great. That's true if there is a benchmark, if the benchmark is published. Why? Because that gives you enough information in equilibrium to evaluate whether the price is good or not. You can compare it to the published price for copper that's available on Bloomberg or on your phone app. You can look at the price that the dealer is offering. You can immediately know whether the price is a good one or not. And the interesting point, of course, is that the bank knows that you know what the benchmark is, and it will only make offers that you will accept on the first go. That's one of the reasons that benchmarks are valuable. They reduce search costs. They also generate more valuable trades. That is, more of you will be willing to shop if you know that you're only going to have to shop once and you're going to get a good price the first time. That means more gains from trade will occur. It also improves matching efficiency, because my bank may not be that efficient at making markets in gold. And if the benchmark is published, I'm not going to be able to get very much trade. I'm going to go out of business because I can't compete when you all know what the best price is. So I'm going to disappear, and you guys are only going to end up trading with the banks that are very efficient at making markets, because those are the only banks that can survive when all the investors like you all know what the going price is. It's much different than what you may have thought about the first time you saw financial market research, which is everybody knows what the price is. You just look at the New York Stock Exchange or the London Stock Exchange or the Eurex derivatives market exchange. You know what the price is. That's not true for more than half, a lot more than half of the financial instruments that are traded in the real world. Most financial instruments are traded over the counter, meaning you've got to find a good counterparty and you've got to find a price at which you're willing to trade. The last point is that because the most efficient market makers will benefit in market share, they're the ones that are going to introduce the benchmark. It's slightly counterintuitive that the banks themselves may find it valuable to introduce benchmarks. They can do it for two reasons. Number one, they get more trades. Number two, they get a bigger market share. So the most efficient banks are going to be the ones that introduce them. Now, in some cases, they won't introduce sufficiently accurate benchmarks. This kind of goes back to our comments about manipulation. They don't have enough incentives to make the benchmarks accurate enough, and regulators need to step in. So in London, the United Kingdom has set up new legislation to protect the integrity and quality of financial benchmarks. The Eurozone is setting up similar legislation to protect the quality of financial benchmarks in Europe. for foreign exchange, for interest rate benchmarks, for commodity benchmarks, and so on. Japan has done that as well. The United States has not done this, and I don't think it plans to do it. Congress seems to be not anxious to step up and perform this additional regulation of financial markets. However, the Central Bank of the United States, the Federal Reserve, is very anxious to see that benchmarks are properly protected and to avoid this kind of manipulation. So that's the end of my comments about price transmission and over-the-counter markets. And now we have some time, if any of you have questions, for Q&A.
Thank you very much. Other questions?
Well, thank you very much for your talk. You were mentioning a lot the fact that incorrect information plays a very important role. Are there models that explicitly try to incorporate the existence and propagation of incorrect information, and can one analyze them? Can one conclude something from them?
Yeah, it's a very good question. So there's very little research on that. In the case of benchmarks, I did some work with a Stanford doctoral student named Piotr Dvorák, in which we analyzed the game between those providing information to benchmarks and those designing the benchmarks. So let me describe briefly how LIBOR and Euribor are done. For those benchmarks, we call the banks on the phone, and we ask them, if you were to borrow money today, what interest rate would you pay? That's obviously subject to manipulation. It's an opinion-based poll. Better would be to have banks perform transactions in which they actually borrow money, but even those could be manipulated. So now what do you want to do in terms of the reports that you get? Turns out that in theory, you'll always have some amount of manipulation in equilibrium, but you can reduce the amount of manipulation if you put lower weight on small transactions, because you don't want to make it too easy to manipulate. And so actually there's a calculus of variations problem, and you can go to my webpage and find it, in which you calculate the optimal weight that's based on the size of the transaction. Unfortunately, the setting in which we're doing this analysis is extremely limited, so I'm confident that many of you could actually do a much better job, and also in particular, you should, in principle, the weights should also decline as the prices get further away from the middle of the population. LIBOR, in the LIBOR and Euribor polls, they actually toss out all the observations in prices that are too far from the median. And we don't know how to do that mathematically, but that would be nice if anybody can solve that problem. There's a question down there.
This is somewhat real life motivated by flea markets, but I notice we have a benchmark like eBay, and we have a fine number of sellers, traders in this case. And half of the people I notice ignore the benchmark. So what happens to the Pandora problem if we have maybe 50% of the consumers who just ignore the benchmark?
It's a great question, and it's somewhat paradoxical. The result that you're describing may be the one that I remember from my colleague at Stanford University, Michael Ostrovsky, who was one of the people that showed that people seem to ignore the buy it now price, and they still go searching. And I mean, I find it unable to explain that, except unless there's behavioral explanation. They even when the buy it now price is very attractive, they seem to ignore it. I just don't know. I mean, it's consumer behavior is sometimes hard to describe, and behavioral finance is a big topic. Maybe it is behavioral. I'm not sure.
There's one more.
Do you see this as having application to dark pools where big banks are trading between themselves and their own customers?
It's another excellent question. So there's an economist at MIT named Hausdorff Ju that's looked at that problem. And it's a very interesting question in the following sense. For those of you that don't know what a dark pool is, I described at the beginning of my talk a central limit order book market at which supply and demand cross at a particular price, which reveals the beliefs of all of the investors in the central limit order book market. Could be Eurex, for example. And then we have these other places where prices are not set. We simply use the prices set on the exchange, but we then get to trade off of the exchange at preset prices. And there's been some accusations that this lowers the price transparency of the market. Hausdorff Ju showed that under reasonable conditions, exactly the opposite happens. Why? Because those that trade in the dark pools know that they could get rationed. The price is not going to clear that market. If they know they're going to get rationed, they're only going to go there if they're very patient. They're not in a big hurry to trade. Those that are impatient tend to be more often those that are highly informed. So now we're going to get a separation. The highly informed are going to trade on the exchange because they need to execute immediately. The less informed are going to trade in the dark pool. That means the exchange is going to benefit from this law of large numbers that I described, where you have the wisdom of crowds all informed on the exchange is going to set an accurate price. And the dark pool is going to rely on that accurate price and not going to produce any more price information. You actually get better price transparency in that example. Now, there's some other unfortunate aspects of dark pool transparency, like the quantities are not reported in some dark pools. That's a problematic thing. But short answer is I recommend you look at the paper by Hausdorff Ju, that's Z-H-U, at MIT, to get some ideas of that question. It's a great question.
Any more questions?
At the beginning, you assumed that the measure on the agents was non-atomic to avoid too large players that by themselves influence the market.
Correct.
Can you comment a little bit more about this assumption, if there is anything done on atomic measures, or how practically close to real life this assumption can be, is?
Okay, so in practice, there's about 200 people in the room, and that's definitely not infinity, but it's reasonably large. The problem is we don't know how to model the evolution of beliefs in the population when there's a finite number of players, because we cannot take advantage of the law of large numbers, and so you have a very stochastic behavior to this measure value process. And here is a confession. This is not anything more than the weakness of the modelers. We were unable to solve that problem. I think it's a great problem. And the reason, it's interesting for two, I'll wait for the jet to go over. Okay, so it's interesting for two reasons. Number one, I can behave strategically when I'm big. If I'm an atom in the population, I could, for example, misdirect people. I could trade, and this is the other question about manipulation, I could trade so as to move the price, and in order to cause people to not understand what the price is. Or I might be more conservative. I might not want to trade very much because I don't want to reveal that I have a lot of information or a big quantity to sell. There's a famous paper by Pete Kyle on how large investors that are privately informed will not immediately trade because they're worried about releasing the information. In the case where you have no atoms in the population, everyone will just charge ahead and not worry about their strategic effects. And that, again, goes back to work by Werner Hildebrandt with the advantages of a continuum. The other reason that atoms are important in my setting is that you can't apply the law of large numbers if you have an atom in the population. That's technical. That's a technical problem. But people would pay. If it was Warren Buffett or some big investor, people would pay very close attention to the prices at which those trades happen, and that would cause the modeling to be very, very difficult. So that's a second question is purely technical. The second reason for not being able to do it is a technically motivated reason. Okay, I think we're
There's
perhaps...
there's one more.
Oh, there's another one.
Yeah,
Okay,
yeah.
great.
I have a related question to this behavioral question. We know there are these models out there like this bubbles model by Abreu and Brunnermeier that actually show that there's not sufficient higher order knowledge, then just a small portion of behavioral traders can actually really kind of skew the prices. Do you have any idea how that works in these models? Because I could assume that, or I could think that it's reasonable to assume that there's not a lot of high order knowledge out in these games there, because, I mean, you know what you know yourself, but how should you know what other people know?
Yeah. It's a great question. Here, as is the case in many, many mathematical models used in economics, we assume that investors are hyper-rational. They can not only solve their own problem, but they can place themselves in the position of all the other players in the market and solve the problems that those other players face in order to help them solve their own problems. And they also can say, well, if that guy knows that I'm doing this, and I know that he knows that, and he knows that I know that he knows that, and so on. These are the higher order effects. You can get, we're assuming everywhere here that these higher order effects are allowed to propagate out to infinity, whereas in the real world, probably most of you don't think too much. You may think about, well, the rest of the investors are doing that. You're probably not thinking too much about whether they know that you know that they know that you know, and so on. That's, you know, economists are not very good at solving complicated problems like that. The paper that you mentioned is an example. There are other papers that address this issue of higher order beliefs and limited rationality. I could recommend some work, for example, by David Krebs at Stanford University. But here, you know, again, confession of the weakness of the modelers. We don't know how to deal with that. So we're assuming hyper-rationality.